So let me start talking about maximal ideals and prime ideals in a commutative ring with identity. This is a big subject. It's much of commutative algebra, which is a central topic in mathematics. So we'll only just give a tiny little introduction, a little more than definitions. Prime ideals generalize prime numbers in Z and irreducible polynomials in one variable polynomial ring over a field. The study of these is sort of the central focus of commutative algebra. And this maximal ideals and prime ideals are actually important for also this following reason in geometry. I mean, this is sort of the main thing, and I'll be rather vague here, but in analysis or in geometry, you often study a problem by focusing at a point or looking in the neighborhood of a point. If you've taken advanced calculus class, you might have seen this many times, and you'll see more as you go along. So it turns out that maximal ideals or the prime ideals allow you to do sort of the same kind of thing algebraically in the subject known as algebraic geometry. So that's sort of the main central reason why they're important. So this was a little introduction. Let's get to business. So before defining maximal ideals, that's all we'll do in this piece, we need a preparation lemma which relates the condition of a ring being a field with something in ideal theory. So R is actually always going to be a commutative ring with identity in this discussion. So here's the statement of the lemma. A commutative ring R with 1 is a field if and only if the only ideals in R are the obvious ones, 0 and the whole ring. Because there is no proper non-zero ideal. So let's actually go through the proof of this. So I have to do two implications. So assume R is a field. Let's go in this direction. And what do I need to show? I need to show that the only ideals in R are 0 and the whole thing. So let I be any non-zero ideal. Let's take a non-zero ideal. What do I want to show? I want to show that I is the whole ring. By the way, you're assuming that R is a field. Let's write that down. So assume R is a field and take an ideal I in R which is non-zero. And I want to argue that I equal to R. See, my ring contains 1. So as long as I contains 1, I is going to contain all multiples of 1, which is all elements of R. So I just have to show that 1 is in this ideal. So that's easy actually. Take any element in the ideal that is non-zero. See, I'm assuming that the ideal is non-zero, so it has some non-zero element. Since R is a field, A inverse exists in R. It has an inverse. Every non-zero element of our field is invertible. That's how you become a field. So since A is in I, and I is an ideal, we have that any multiple of A, for example this multiple, is also in I. But what is this multiple of A? It's 1. So 1 is in I. So for any if you give me any B in R now, then I can write B as a multiple of 1. And because 1 is in I, any multiple of 1 is also in I. So R is I. That proves this implication. Now the other one is also almost as simple. What have we now? We're having a ring, a commutative ring with 1, whose only ideals are the 0 ideal and the whole ring. So assume only ideals in R are 0 and R. And what do I need to show? I need to show that R is a field. How do I show some ring is a field, a commutative ring with 1? I want to take an element and show that it has an inverse. So take some A in R and better be non-zero. So I take a non-zero element and I need to find the inverse. What do? I know something about ideals. Given this A, can I cook up an ideal? Yes, I can. So it's called the principal ideal generated by A. So consider I be all multiples of A, also written like this, remember? And this is an ideal. Then this I is an ideal, and it's non-zero because A is a multiple of A. So it's in my ideal I, and A is not 0 by my choice. So I is not 0. So here is a non-zero ideal, I. What's the conclusion? So I is the whole thing, whole ring. In other words, AR is the whole thing. So 1 belongs to AR, i.e., what are all the things in AR? They are all things that look like A times B. So 1 looks like A times B for some B in R. But that just means that A is a unit. This B is now an inverse of A. A is an unit in R. What did we argue? We argued that every non-zero element in R is a unit, so R is a field. That's the proof. And once I have this, I can make my definition. I mean, I don't need the lemma for the definition, but for the first result that we'll state. An ideal, a proper ideal. A proper ideal M in R is called a maximal ideal if, and I'll remind you, R is still a commutative ring with 1. A proper ideal M is called a maximal ideal if whenever I is an ideal of R and I contains M, then I has to be either M or R. Meaning, you have R, you have M, you cannot find one that is strictly bigger than M. You cannot find another ideal which is strictly bigger than M but strictly smaller than R. That's the meaning of the word maximal, okay? That there is nothing that is strictly bigger. So if you do get something which is in between M and R, then it better be either M or R. In other words, you could say that M, there is no proper ideal that properly contains M. In other words, there is no proper ideal. Proper ideal means ideal that is not equal to R. In R, that properly contains M. Properly containing meaning containing but not being equal to it. All right. So that's what a maximal ideal is. And the lemma that I'm going to state tells you how to recognize them. An ideal M in R is maximal if and only if R mod M is a field. And the proof of this uses this first lemma that we proved. That's why we proved that. In fact, maybe if you wanted examples, first example, when 0 is going to be a maximal ideal in a field because it's a proper ideal, and in a field the only ideal is 0, so it's a maximal ideal. And the proof of this is pretty much proof of this lemma. It follows immediately from the earlier lemma and the correspondence theorem that I have quoted up on the right here. Remember, the correspondence theorem says the following, that if you have a ring and an ideal M, you can go to the quotient ring. What happens when you apply the quotient map, or the quotient homomorphism, is that all of M gets squashed to the 0 element. We call this S. This is all the 0 element of S. And the ideals that are in R and above M correspond to ideals on the right hand side. So if you give me an ideal in S, I get an ideal in R that contains M. If you give me an ideal in R that contains M, then I take its image and I'll get an ideal in S. So now how does that help? So do not M is maximal in R if and only if there is no ideal strictly between M and R. There's nothing in between here. There's no ideal like this. But that's same as saying that there is no ideal strictly between the 0 ideal and R mod M in R mod M. And this equivalence is using the correspondence theorem. Because I know how to compare ideals in R and ideals in R mod M. Okay? But then there is no ideal strictly between 0 and R mod M means R mod M has only two ideals, 0 and R mod M. And by our first lemma up on the left here, this is same as saying R mod M is a field. Okay, so that's roughly the proof. Maybe one should write a little more detail, but we'll write that down in the notes. Okay? So we can use this next time and give some examples of maximal ideals, and we'll go on from there.